Okay, guys, so let's continue from where we left in the previous class. So, just to summarize that, we modeled your hand motion as a particle pendulum as a summary, because I'm not done yet. And we ended up with nonlinear differential equation theta double dot plus g over L sine of theta was 0, and we linearize around equilibrium point of theta star, equilibrium point of 0, and we got theta double dot plus omega n square sine of theta is 0. And this was our linearized differential equation. I'm sorry, guys. Theta. Okay. Theta was 0. Okay. And we had a classical solution, and we got the final solution of your hand angle as like d, if I remember, sine omega nt, minus phi, right? So it was showing that your hand gonna oscillate forever like this, if this is the angle of your hand, theta, versus time. And we had two roots, remember, S1 and S2, while solving this differential equation as plus minus I imaginary, pure imaginary omega n. And in the complex plane that I showed you, and we're gonna deal with this in this course and also the control course that I'm teaching. So it's imaginary, it's a imaginary axis and the real axis, and then you have a pair of pure complex roots or poles that we're going to define later. And we judge that whatever is the dominant poles, I'm saying I'm going to define this later. What is dominant? Dominant roots here and poles later that I'm going to define. Dominant poles, they are on the imaginary axis, means that your system is what I told you? Your system is marginally stable. Marginally stable. It's not unstable, it's not stable, but it's marginally stable because oscillating forever. Okay? Now, before going to the MATLAB, we have to finish this topic, and then I will go to MATLAB, then I'm going to go to the Laplace, because after that I don't want to stick to the classical differential equation, because it's going to be funny if I apply impulse as an excitation to the system. Impulse. Okay? I will explain why later. We are transferring from, write it down. This is time domain. Okay? This is time domain because you have time to restrict. In this class, we're eventually gonna travel from time domain to frequency domain, omega. And we're gonna analyze the system in the frequency domain using the Laplace transform. Okay? So, before again going to the MATLAB, we have to finish this topic and give you a good sense of stability on the systems, because in the first order system and second order system or higher order system that we're gonna model, we have to deal with this. Now I'm gonna invert this particle pendulum. Do you know what this is model of what? Do you know what is the model of what? Give me the answer. Just brainstorming. This is model of what? You can say this is model of which system? Hmm? Any idea? If this is your hip joint, you can say this is my upper body and this is my head. See what I'm saying? Can you hear me, guys? Hello? Yeah, good. So if this is your hip joint, you can say this is my upper body and this is my head. Interesting, right? And exactly your body can be modeled as pendulum and inverted pendulums. Two hands and the pendulum, two legs as a 2 degree of freedom pendulum, your upper body or torso as the inverted pendulum. Interesting. And exactly you have joints in your body that can be modeled by designing controllers that I'm teaching in ME530. Okay. I may hint here in this course, but it's not the main focus of this syllabus of this course. I'm teaching you how to model variety of different system, analyze it, and this kind of things. Okay. So this is L again, say, and this is M. I'm assuming the mass of your upper body is lumped at your hand. This is just simplification. So this is inverted pendulum. Inverted pendulum. Here we go. Here, to this plus, I'm circling it. I'm going to tell you why later, today. Okay? So today, I'm going to emphasize on this side because throughout the whole course, and even after you graduate, you have to be careful of the signs in differential equations. Signs have meaning for control engineers, for mechanical engineers that they are working in the field of control. Okay? So, what we have to do, you have to, again, find these. Here gonna be L cosine theta from kindergarten trigonometry, L sine theta, and the mass of this is being applied, weight of your upper body, mg, and say you have a reaction force in the hip joint of your body. Say here like this. Here we go. Now, as I taught you in the previous class, because hip joint is stationary here, has no motion, you can apply what? You can apply moment equation. Sum of the moment around, say, H, I'm saying hip point. See, I'm modeling the body as the inverted pendulum. Around H, hip joint, is I of the mass around hip joint and the angular acceleration of your upper body. You're gonna give me what's the example of this? Michael Jackson when he was dancing. Okay? Michael Jackson upper body was doing like this, oscillating. Okay? So, as we concluded, this Fy and in Fh do generate or do not generate any torque around point O. Give me answer. I taught you in the previous class. Yes? So this Fx and Fy do generate or do not generate any torque or moment around point H. Yeah, because it's passing through the points, right? So again, like as the previous case, only mg generate. So, and it is mg in the normal distance. Normal distance means this. L sine theta. L sine theta. Based on what I was taught in the previous class, what's the sign of this? Positive or negative? Help me. I told you resisting the motion is negative, helping the motion is positive. If you apply mg, what's gonna happen for theta? Increasing or decreasing? Increasing. So it's helping the motion. Plus. Everybody understand this? Yes? Because we want to increase theta. Applying mg, it increases theta. So helping the motion is positive. Simple like that. You don't need to go for clockwise, counterclockwise. See what I'm saying? This is sense of engineering. Clear, guys? Everybody? Yes? And from the previous class is ml squared. I don't want to repeat myself because this is particle. I did in the parallel axial theorem. Is ml squared theta double. Okay, we got the differential equation. If you are done, I'm gonna move to the next page. Can I? Yes? Guys? Okay. So, having that, let me stick here. I'm gonna remove this m with this m, this L one of this, and what you're gonna have is L theta double dot equals to G sine theta. Or if you move and divide both sides by L, it's gonna be minus G over L sine theta is 0. And here we go. This is your nonlinear differential equation by inverted pendulum. Now I'm circling this sign, negative. Look at the regular pendulum plus this sign negative. Now I'm going to talk about this a lot because when I go to the row stability criteria in this course, you're going to see these signs, they have rules. Okay. So now I'm saying omega n again is G over L, right? See what I'm saying, guys? Natural frequency, remember? Can I, guys? Yes or no? Obviously no. Here I can't. Why? Because everything is based on trivial mathematics. Let me solve this. Your upper body motion again is EST. So you know that E theta dot, look at the previous class, SEST, and theta double dot is S square EST. If you just replace here and factor out EST as we did previously in the previous class, is S square minus G over L is 0. As I taught you, this cannot be 0 because it yields a trivial solution. So what you get is S square is G over L. Or now you have two roots or two poles. S1 is plus G over L. S2 is minus G over L. Guys, all of you look at here, don't write, I give you time to write. What's the difference between the roots or poles of this system and regular pendulum roots or poles? What's the difference between them? Yeah, these are real poles or real roots. These are real numbers. But those are imaginary numbers. So if you see that any system, this is take-home message, as I told you in the previous class, any system has only pure imaginary poles or roots, it's gonna oscillate forever. So do you think this is gonna oscillate forever, this system? No, because these are reals. So that's why, because the system doesn't oscillate, we don't have natural frequency because there's no sine or cosine, and I'm going to show it to you. So if, yeah, go ahead. Exactly. And to clarify, if the system only has pure imaginary, not among them, because any system can has combination of real and imaginary together. I'm going to show it eventually. Okay? If system only has this kind of roots, imaginary roots, only this. See what I'm saying? Maybe a system order is 4. I'm going to show it eventually in this class. And you have 4 pair of imaginary roots. See what I'm saying? So that system gonna oscillate forever. But when your system has, oh, why this came here? When the system has real roots, it says your system never oscillates. Okay, bear with me because I'm not done with mathematics. I'm gonna summarize everything. So we found the roots I'm gonna implement here. So theta of your upper body gonna be A constant, E your first plus G over L T plus B E minus the other roots or pole G over L T. Okay guys, these are real numbers. Now you let me know. If I increase T to infinity time to a large number, what's gonna happen for this term? This is from high school. What's gonna happen for this term? This goes to how many? 0. And what's gonna happen for this term? This is plus G over L T. To go to large value, that's right? Yes? Yep, so I say infinity, a large number. So you see, not only if I plot this, system doesn't oscillate because it has a real roots. So theta versus time, it cannot go. So in the terminology of the control and robotics and dynamical system, we name this system what? Unstable. Oh, so the roots or poles of the system that showing internal dynamics of the system from right hand of the system. Guys, we have to linearize it. I forgot to tell you. Again, we linearize. Yeah. Again, I cannot hear you. Yeah, exactly. I'm going to show it here and in MATLAB. Okay. So you saw that. Now I have a meaning. The first thing that I'm going to eventually teach as a rule, as a Rolls stability criteria rule, is that if the first condition that your system is stable, first condition is not all, is the all signs of differential equation that you're dealing, I mean linear differential equation, be positive. Here is positive, but it doesn't have the second condition that I'm not teaching yet. I'm not teaching yet because it's not the time. But here, one of the signs is what? Negative. So your system is not stable. Even by looking at differential equation, you can say, oh, like, let me tell you this one. For example, you say if theta double dot plus 100 theta dot minus theta is 0. By looking at this differentially, just only by looking at, not even analyzing. Okay? What happened? Okay. Not by analyzing. See? You say, oh, This is negative. Our system is unstable. We have to fix it. It's gonna blow up. And this is powerfulness of mathematics. And I'm gonna teach in classical way. This is just giving you a big picture. See what I'm saying? Yep. So now let me go to the complex plane. New slide. What is this? I don't want to have you. Oh! I want to remove this, guys. Okay, whatever. Okay. So if I plot that in the if I plot that in the complex plane, real, imaginary. Okay. So we have real roots. Okay. One of them is positive, this, say, here we go. Another is negative. And both are real, so they're gonna locate it at the real axis. And as I taught you in the previous class, as a picture that I'm gonna show it mathematically, not by only saying, whatever is in the right hand side showing that your system is unstable. Whatever is in the left hand side shows your system is stable. If your system. And whatever is on the imaginary axis shows your system is marginally stable. Means oscillating forever. But you see that your inverted pendulum, as a model of your upper body, has two roots. One of them is located in the right hand side, saying that your system is unstable, it's blew up. Remember, in the regular pendulum, you had this a pair of pure imaginary roots or poles. You see, by changing the position of the roots or poles that we're going to define after introducing a Laplace transform, you can judge about the internal stability of the system. See what I'm saying? Now, even without, yeah, go ahead, ask us. When we go to the Laplace transform, we're going to rename roots as poles and zeros of the system. Okay, see? So now we suppose that you have no knowledge of that. Now, based on whatever I taught you, so what do you think about this system? It's gonna be stable or unstable? And even you don't know what's the system. It's a pizza, it's kebab, it's car, it's satellite, whatever it is. Stable because they are in the left hand side. What about this system? See, third order system means has three roots. What about this system? Unstable because one of the poles or roots is in the right hand side. See, you can't judge the system even by looking at what is located in the complex plane. So when you come to ME430, your function is to move this roots or pole to the left hand side. Say you have to push it to this area or to this area, whatever that you want. This is the big picture of control engineers for linear systems. See what I'm saying? So, for example, for this margin stable system, if you want to make it stable, you have to design a controller, say, push to this area. See what I'm saying? Or, yeah. See what I'm saying? For example. So, now we know everything. we know that the signs of a differential equation speaks with you. Says, oh, I'm fine. Oh, I'm blowing up. See what I'm saying? Yes? So now let me go to the MATLAB and simulate whatever I have done until this point before going to Laplace transform. And so after doing this, I'm going to go Laplace transform. Laplace transform. Then I'm going to go to the first order systems eventually. Then second order systems. Then higher order systems. Then electromechanical systems. This is going to be very challenging. Electromechanical fluidic system. Fluidic system. Okay? See what I'm saying? And finally, and inside here, may I discuss the thermal system. Thermal system. Okay? And we continue the class like this. Okay. Now, before going to the MATLAB, I have to teach you another tool that you can use in MATLAB. Okay, guys. The name of the tool that you have to know, maybe few of you know that you had vibration course with me, but for those that you didn't have vibration with me, I have to teach you. So, the name is state space equation. State space equation. Equations. Okay. So, what is that? I'm introducing by the ridiculous problem that we had here. Pendulum. Pendulum. In a state space equation, we define state variable. Let me teach you. We define state variable. This is technical name. State variable means that I'm saying M1 exactly. I'm gonna do this in MATLAB. What you see, I'm just copying there, is angular position of the pendulum. And the M2, these are state variables, M1 and M2, is the angular velocity of the pendulum. Now, what these are the state of the system, that's right. How it stands and what's the velocity of that. These are state, like as your car. What's the position of your car? What's the velocity of your car? These are states of the system, dynamical states of the system. Then I'm going to have a time derivative from the both sides. So you're going to have d means differential equation, time derivative. dm1 is equal to theta dot. So what is theta dot, guys? What is theta dot? Look at here. What is theta dot? No. What is theta dot? Yeah, what is theta dot? Just look at here. Yeah, it's M2. Exactly, I'm going to type this in MATLAB. See what I'm saying now? Yes? So here, the M2 gonna be theta double dot. So what is theta double dot? Bingo. You can find from here. Theta double dot is minus omega n squared theta, or minus omega n squared. What is your theta? What is your theta? Yes, M1. I'm just putting here minus omega n squared m1. I'm rewriting here, guys. dm1 equals to m2. dm2 equals to minus omega n squared m1. The name of this in control is state space equation. Bingo. For any dynamical system, you can do this. And MATLAB understands this language. See what I'm saying? Yes? Good. So, yes, go ahead. So it's differential equation understandable for MATLAB based on your state variable. Your state variable are the position and the angular velocity of the pendulum. Bear with me. Or linear position x, like a position of your car. Or linear velocity of your car, x dot. Or, what? Yes, I'm not going there yet because I didn't introduce the multi-variable Taylor series expansion. I'm going to do it later. Okay. And the Jacobian matrix. Okay. I didn't introduce yet. But they are, yes, they can be written in a matrix form. Okay. See what I'm saying? So, or if you are dealing with the control of pressure of a tank, state variable is gonna be P M1. M2 gonna be what? Based on whatever I taught? Look at here. M2 gonna be what? This is pressure. M2 gonna be? Well, yes. Rate of change of the pressure. If you are dealing with the controlling temperature of a room, M1 gonna be temperature T. M2 gonna be what? T dot. See what I'm saying? Yes? If you have a tank of the water that I'm gonna teach eventually in this class as a first order system, and you want to control, as control engineer, height of the tank of the water from the bottom, so M1 gonna be what? H. M2 gonna be what? Tell me. Look at this. M2 gonna be? Yes, H dot. If you wanna control the amount of pizza that you are eating, M dot gonna be pizza. M2 gonna be what? Pizza dot. I'm not kidding. The rate of change of pizza that you are eating in unit time. Okay? See what I'm saying? So don't say Professor Musawi taught us only theta theta dot. No. If you are trying to control the position of your car, so you're gonna say M1 gonna be X, position of your car, M2 gonna be what? Velocity of your car, X dot. Everybody crystal clear? Yes? Good. Good. So, now having the state space equation, can I go to next page? Yes, guys? Okay. So while we have state space, right, this is recording hopefully, yes, yeah. So now we have state space equation. When we go to the MATLAB, hopefully this class, okay, you see that I am, because the differential equation speaks with us. You are graduating eventually. When they ask you what the zero means in the right hand side, what does it mean? These are trivial things that you have to know. What does, no, this is differential equation of kebab, Persian kebab say. Okay, forget about the pendulum. So left hand side shows to you what? These are, did you pass the differential equation? Okay. Left hand side shows internal dynamics of the system, like stability and instability. Okay, in internal dynamics of a system. What right hand side shows to you? These mathematics, they have meaning. If you don't know the trivial basic meaning, you are not engineer. I'm not kidding. No. This shows forces or moments or excitations or controllers that we apply to system to control it. See what I'm saying? Like if I have a torque here, like as designing controller, tau, to set the position of this mass to angle, say, pi over 4, 45 degree, you need a controller. This controller sits here, tau, torque. See what I'm saying? Yes? Man, we discussed a lot, remember? This is internal dynamics of the system, gives you how the system behaves. Yeah, by itself, without applying any external force, without applying this. You want to see how system behave by itself. Okay? See what I'm saying? So now if you want to add a controller to control the system state, the system position, the system velocity, the system angle, the system angular velocity, the system pressure, the system temperature. For example, now you are sitting in the room has AC, that's right? Yes? Room has AC. To control the temperature of the room, yes or no? Yeah? Then there's a box there to control the temperature, yes or no? Yeah? Okay? Guys? Can you hear me? Okay. That box sits on the right hand side. See what I'm saying? Because by that box you are controlling the system. You are applying temperature to this room. See what I'm saying? Clear? Yeah. For here, yes. For this pendulum, yes. Because by torque, I want to control the angle of this pendulum. See what I'm saying? Huh? So the simplest version of this is this. Let me tell you. Suppose you have a Lamborghini and you are inside, sitting there. So forget about the friction of the road. So what's the? This is very super trivial from high school. Okay. What's the differential equation of the car? Sum of the forces in x direction is mass of the car, acceleration of the car. Yes or no? Yeah? See what I'm saying? So mass of the car, acceleration of the car equals to. If you leave here 0, does your car move? No, no. Just ignite your car engine and leave it. Does it move? So what you gonna do? Tell me exactly, physically. If you wanna make your car move, what you gonna do? Force by what? By pushing the gas pedal. That's right. Yes. Yes or no? Okay. This gas pedal is the force that you are applying to the car to move. See what I'm saying? Okay. And when you increase this pushing more gas pedal, it's gonna accelerate more. Simple like that. So the left hand side shows the force that you are applying to move the system or change the system state, and the left hand side is the system by itself. Clear, guys? Everyone? Yeah. So every day that you are driving, you are solving a control problem. Every day that you walk, you in any millisecond you're solving a control problem. Your body, if you leave it, never moves. But you apply torques to the joints of your body to make it move. See what I'm saying? Exactly. So couch never moves. So the couch dynamics is this. Mx double dot is 0. And that's why it never moves. See what I'm saying? But when you start to push the couch by your hand, you are controlling that. F. See what I'm saying? Clear? Yeah. Control command. I'm gonna teach it eventually. Okay? Control command. When I plot block diagram, eventually I'm gonna teach it. Okay? It's a control command. Okay, guys. Now where we were. Can I delete this? Because can I? Okay. Yeah. So now we have the state space equations in MATLAB. Here we go. Here we go. But because our system, we assume that there is no controller from the beginning. It's free motion of the system. Here was 0, remember? Yes? So now guys, please experiment that at home with me. If I start the pendulum from here, like your hand, put parallel to your body. So if I start from this position, does it move? Do it. At theta 0, I'm starting from at theta 0. And theta dot, angular velocity of the 0. Does it move? No. So I have to define in MATLAB, we name it initial conditions. Initial conditions. In MATLAB, we have to do that. I'm releasing from this position. I'm saying, you know what? Initial position of the system, theta naught, is pi over 4. In MATLAB, we have to write in radian, not in degree. Okay? And okay, I'm saying the initial velocity of that is 0. Or we have to define in MATLAB like this. M1, initial position. Okay, I'm gonna show it how. Is pi over 4 initial position of that. And the M2 is 0 for initial position. Clear, everyone? Yes? Yes, guys? Good. Now, let me go to MATLAB. Okay. So what you're gonna do in MATLAB, you have to, for those of you, let me redo it. That is the first time you see MATLAB in your life. So you have to go to new script because we are coding in MATLAB. So it generates an environment for you. The name is editor. Okay. So, and this is how you're gonna do. If you want to type a differential equation in MATLAB, you have to say function. See, it becomes blue. This is a command in MATLAB. So what were your state variables? Look at your notes. What were your state variables? Look at here, guys. See? But DM, I mean generally DM. See? DM1, DM2. See what I'm saying? So I'm saying exactly the same here. See here? Differential of M equals to, you have to write like this. I'm naming this M file. We name it M file. This coding means M filing. I'm gonna show it to you. Like as I say, pendulum, whatever you want. Pendulum ana means analysis. So you are, and now bracket. So now you are in the time domain. So we are saying T. MATLAB knows this, time. And your state variable is M generally. Here we go. And then this. Here we go. See what I have done? If your state variable is X, by any chance, you have to do this, T and X. If your state variable is Y, T, X, and Y. If your variable is H, height of the tank, as we're gonna do eventually, TH. But generally, you can stick to this M because it doesn't change the system identity. Okay. Now we are dealing with the pendulum, and this is our differential equation. Okay. Here we go. Here we go. Oh, where's that? Here we go. So we have to type this, but we need omega n for the system. So we're gonna define it like that. I say omega underline n. I don't know, is 5, and I can comment it by this, 5 in radian per second. I'm commenting my code to don't forget the details of my code. Okay. Now you can push control. You can hold control and push S. Okay, I'm going to ME430. This name, you see that MATLAB code files, M file. Do you see this, guys? Do you see this M file? Okay, you cannot change it. This name exactly must be the same as this name. If you change it, it's gonna give you syntax error. So I'm not changing. Pendulum underline analysis ANA. Save. You see the file name changed. Pendulum underline ANA. Clear, everybody? Yes? Good. Now I'm going to state space equation. As I type dm1, is m2. dm2 is minus omega, as I defined here, n square multiplied by m1. Here we go. See, guys? Exactly as I wrote here. So MATLAB understands state space equations. But you have two state variable. You have to make a space for that. You're gonna say dm, as you define here, is zeros 2 and 1. So let me see what the 0 does in MATLAB. Look at here. I'm copying and putting oh, because I did this. Okay, look at here, guys. Zeros, 2 and 1 gives you a column of 2 zeros to generate the state variable. This is how you do in MATLAB. If you have 3 state variables, you have to say zeros, 3 and 1. Zeros, I don't know, 10 and 1. For example, the robot, the quad rapid robot that I have in the lab is 18 degree of freedom, means has 36 state variables to control. So you're gonna hit 36. Okay? This is how MATLAB understands things. So now you generated the state variable space for that. So now let me open it. Okay, you see that? Now we have an M file here saved already. Okay, so now we have it. Now we have to go solve this differential equation. I open another new M file, new script here. Now I'm saying, okay, total time that you want to run the simulation and the output of the system, say, is theta, angle of that equals to, okay. So you're gonna say ODE means ordinary differential equation solver, because this is ordinary differential equation from differential equation course. We name it ODE. So ODE, this is how you have to do that. Bracket at in MATLAB means go and run the other M file. Which M file? M file that we did it. Peng analysis. Now this code gonna call the other code and run it. Okay. Okay. I say we have an initial condition. What was the initial conditions? I told you. Where is that? No, I mean that pi over 4, 0. That's right. Is pi over 4 and 0. Oh, pi divided by 4 and 0. This is how we define initial condition. And I'm saying, okay, run it for, let me say time, because I can't change it. Let me do it. I'm saying time is from 0 with a step size of 1 millisecond, let me do that. 1 millisecond, okay, or 1/10 of the second, and run it for 10 seconds for me. Here we go. Oh, this must be 2 dots. Okay. If I do this, okay, first let me save this. You have to save this file at the place that you saved the previous file. If you don't save it, it's gonna give you error. I'm saying solver. You can name whatever you want here. Solver of pendulum analysis. You can say solver of Michael Jackson. This is arbitrary. Saving. I saved. So you see that what does this do? Let me show it to you. Look at here, guys. If I do this, here we go. It generates, see, a vector from 0 to 10 for time. 0, 0 to 1, 0 to 3, 4, 5, 6, until it comes to where? To 10 seconds. Clear? Yes, this is how we do math. Yeah. Because step size is 0.01. Divide 10 by 0.01, it gives you 1,000 numbers. Okay? So now, I'm gonna plot it. Figure, MATLAB understand. Number 1, plot command. Total time. Total time is now this, because total time goes here. Total time. Now, theta. How many state variables you had? 2. That's right. So you're gonna do this. Guys, look at here. This is the position of that, guys. Here we go. And the color blue. Why I'm doing this? Because it gives you as a matrix the solution. This sign says me go and read all the rows. This give you the first column. How? Hold on here, guys. I'm pushing the pause command. Why? I wanna do something for you guys. Okay. Let me I make it. What's the new version of MATLAB is? Okay, whatever. Okay. So if I run this, change folder, it gives me some error. What's the error? Oh, ODE45. Oh my god. I forgot to tell you, ODE45. Okay? This is solver. Don't ask me why. We have different solvers, like as ODE15, 15S, 113. Okay? This is not the syllabus of this course, but you by default put 45. Okay? Oh, another error. What? May I misplace this, huh? What's wrong? Oh, man. No. So, I think this must be like that. I misplaced everything. Yeah. So, when I run this, guys, let me go up. Okay. See, theta is 2 columns. First column is angle. The second column is angular velocity, or M1 and M2. So if you want to plot all angles, you have to say go and read all the rows and first column. See what I'm saying? If you want to plot all the angular velocity, you have to say go and read all the rows and second column. So exactly what we did here. Where is that? Yeah, here we go. Oh, I have to pause it. Okay, here we go. Oh, I don't want to show it yet. Okay, see? I'm saying plot all the rows. This means all the rows and the first column. This shows you the angle. See what I'm saying? Yes? So let us run it now. Oh, I have to remove this stupid thing. So I don't want to have a pass. Okay. Now let us run it. Oh, exactly as we expected. These are in the radians, the y-axis, and this is time. And it oscillates forever, as we did in the analytical solution. Now you can play with that. You can say, okay, and line width, and make it a little, line width is 2, make it more visible. See here, guys, here we go. And then you can say grid it, because I want to have a scale. Here we go. And then you can say X label. X label is time. And the Y label is theta. Oh, what the hell was that? Okay, is theta. And you have to put like this. Here we go. See? Theta, time. And obviously you have to put units, second, and here is radian, and here is radian. But you can make it to degree. How? You know from high school. You have to multiply the angle by 180 divided by pi. If you do that, you're going to have degree. Please do it here, okay? Initial condition must be in radian. Never do that. You have only in the plot you can do that. Now look at here. Is 45 degree coming to minus 45 degree and oscillates. Now theta is in degree and time in seconds. Clear, guys? Yes? No, this is theta because this is first column. Now in this, yes, now exactly I'm copying everything. I'm putting on the figure number 2. Now if I want to plot the angular velocity, you have to make this 2. And you have to remove this because this is for angle. And now you have theta dot, that's right. Say, I'm not sure because I'm going to teach you the next class, okay? And it's going to be radian per second. Okay? See, dot theta. I'm going to show it how to fix this in the next class. But this is now angular velocity in radian per second. Starting from 0. Why starting from 0, guys? You tell me. Because initial condition we set it to 0. Clear, guys? Everything? Yeah? Yeah, it's starting as pi over 4 or 45 degree. Look at here. So this is figured. This is angular velocity starting as 0. This is how you give system, and this is starting from 45 degree. If I change it to 60 degree or pi over 3, here we go. This is angular velocity again, not changing. It's starting from 60 degree. Even you can change it. You can say, you know what? No, I have a initial condition for the angular velocity is say 1 radian per second. Here we go. See, starting from 1 angular velocity, and this is again starting from 60. Okay. Now, if I increase, guys, because I'm in the trivial steps of the coding, I'm gonna work on this a lot next class. If I increase the natural frequency to 20 radian per second, what do you expect to see of this pendulum? Yes, exactly. There we go. See, because you are increasing the natural frequency of the system. And you know that. I taught you. You have in your notes. Natural frequency is being decreased by inverse, proportional inverse of the L, length of the impulse. On the other hand, I reduce the length of the pendulum to increase natural frequency. And you're going to have faster oscillation. See what I'm saying? Yeah? And if you decrease that by increasing the length of the pendulum, as I taught you, to, I don't know, 1 radian per second, you're going to have a slower oscillation. Here we go. Okay? I'm going to work on this next class because I have to, at the same time, I have to make movie of pendulum and inverted pendulum together to give you a real movie of the oscillation and the unstable system of unstable system. So the next class I'm going to devote on this before going to, because if you understand this code that I'm going to expand the next class, I'm going to share with you by email. If you understand how to code it, the rest of the class you can even that you graduate, you can make a movie of any dynamical system that you can express in differential equation. Okay? Okay, guys? Have a question? So, first of all, MATLAB has no tutorial. MATLAB has, see what I'm saying? There are some books, stupid books, but if you open the MATLAB, okay, you see here, guys, there's a help. If I say ODE 45, it brings you. Click on that, okay? It gives you how exactly works. Time span, initial condition, and going by examples. See what I'm saying? See? Oh, I'm sorry. Hold on. Okay, can you see it? So if I say ODE 45 here, see here, ODE 45, and I click on that, okay, see ODE 45. It gives you how we define ODE 45, time span, initial conditions, and giving you many examples to run it. See, examples. See, and if you follow that, you're gonna learn that. Lots of examples. If I say, what about plot command? See, plot line 2D. See, plot X and Y. Explain what's the command. Give you some trivial examples. See, trivial examples, and you can follow like that. The best tutorial for MATLAB is MATLAB help section here. Okay, understand? Okay, so guys, let me first